Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 13. Students, inshallah, in this lecture we will cover the remaining part of the square footing, as well as we covered that footing in Excel sheet, and we will also discuss a little bit, if I have time, the detailing of the slave reinforcement, okay, in Excel sheet. And as well I will discuss about a little bit about the tributary area in Excel sheet. Okay, so this is very informative lecture. Don't miss this lecture. Okay, so here we have basically we start our lecture number 12. Okay, we were talking about the critical section. Okay, so this is my critical section, okay, which is basically present at the face of the column. Okay, so here you must understand that I already mentioned that loading is from downward side. The footing looks like a cantilever beam, inverted cantilever beam. Okay, and here we have basically these bars which is bent. Remember this, the beam bends looks like in this direction, so these are the bars which are in tension. Now in tension we need development length for the bar to develop its full strength. Remember, you see in the calculation of ASMD, we using Fy equals to 60 ksi. What does it mean, 60 ksi? 60 ksi means that this bar should give me a strength of 60 ksi. For example, remember, what is development length? If you go to my channel and find out my playlists, in playlist here you see this button, and you check this playlist, you see here these lectures which is available on my channel, and here I basically covered an example development length for negative reinforcement or cantilever beam. So this will be an explanatory lecture regarding to this topic and development length. Okay, now the development length of a bar is that length, that embedment length into the concrete. Basically it is the embedment length. The embedment length of the steel which is provided into the concrete to develop its full strength, that is 60 ksi or whatever the strength of the steel is, but that length which develop this strength is called development length. Now this is called LD. Remember this, we have to check whether this length is available. This means that for how much distance this overhang is, okay, and this length we must need to determine. Remember, we already know this length and we calculated this length. This length is from the face of the footing is 3 feet, but keeping 3-inch cover, so this distance 3-inch cover, it will be then 33 inches. Clear? This is the space which is available for the steel. Now we have to check the development length. We need to calculate LD. So to calculate LD, okay, we have Nielsen book at the end and a table. From that table we can easily calculate our LD. LD divided by dB, we find out this ratio from Nielsen book ACI table. Okay, and this is for tension, remember, and 38, and once we find our LD, okay, multiply dB is the diameter of the bar. We are using number 4 bar, so that why 38 times 4 divided by 8, we got 19 inch. So we needed 19 inch development length LD, and as the available space is 33 inch, so that why 33 inch is more than the 19 inch, so that why the development length criteria for tension is satisfied, and we don't need to provide a hook. Okay, if this is greater, so we have different arrangement. We provide a proper hook. Okay, this hook should be designed, and how to design, I recorded these lectures regarding this this hook design. Okay, and if it is not satisfied, then there are other arrangement. We have to change the bar size, we have to increase the this overhang portion. Okay, so there are many arrangements we can do that calculations. Okay, so let me show you the Nielsen book and this table. Okay, here we have development length for tension. Okay, this is for tension, LD divided by dB, and you see we have 60 KSI steel, and we have 38 for, because we are using 4000. Clear? And remember this one, number 6 and smaller bar. So as we are using number 4, so that why if you are using number 7 and larger bar, then you have to use these tables. These case A and case B I explained thoroughly in these lectures. Please watch those lectures. Clear? And now you see the development length for compression bar. This is also important. Clear? This is also, although I don't check that reinforcement, that check. Okay, so here let me show you that how we can check the dowel bars. Okay, compression bar. And here you see we already explained this. Okay, and now let us we did a little bit discussion about the dowel bars. Remember, whenever we are placing this column on this footing, so what we have, basically we are transferring compression stresses to the footing. Okay, compression stresses to the footing, and they're causing, basically at this region, causing bearing stresses. Remember, and there should be such amount of area available to this column, that those bearing stresses should be safely transferred to this footing. Okay, if the area is small, then what will happen? Remember that then the bearings failure will occur. Okay, so for that purpose we calculate bearing pressures or bearing stresses by Bn, and ACI defined formulas for these, and I will show you in Excel sheet this formula. If our PU, that is less than pi P and B, that lesser than the bearing pressure, we don't need dowels. Okay, this means bearing pressure will be easily transferred safely transferred to the footing. And if this criteria is not satisfied, what we have to do, we have to provide, basically what we have to provide, dowels. Okay, then by dowels we will safely transfer those bearing pressures or bearing stresses safely to the footing. Okay, so let me show you the dowels. Okay, let me show you, for example, you see in this video, remember in this video you see that basically this hook is provided, and this bar these are basically called dowels. Okay, and then the rest of the portion of the bars of the column will be left, okay, in compression with these dowels. So this hook is provided, and we have to calculate this reinforcement, whether these bars are needed or not needed. So let me show you, if PU is greater than pi P and B bearing pressure, then we need to calculate properly the dowel area. Okay, and if it is this criteria satisfied, then ACI explain that that you have to provide minimum dowel area, and minimum dowel area is 0.5% of small area, means area of column, that is 12 cross 12. Okay, that is 144. Now the dowels are basically placed here. Okay, the dowels are placed here, not here. The dowels are basically right, we extend this and we provide hook this. Okay, and similarly we extend this and we provide hook this. Okay, so this length is basically called the development length in compression. This is denoted by LDC. Remember, this hook length is not included in the LDC. Remember, and ACS is basically defined that this hook having no role in compression. Okay, in compression splices. Remember, this is very important. But if this development length is not satisfied, then we either increase the depth of the footing, thickness of the footing, or we provide this hook. Okay, they work a little bit. Okay, now we have to calculate this LDC. Now this length is basically nothing. You see, you already know this thickness, that is 12 inch. So 12 inch minus, we already provided 3.5 inch effective cover. So you understand that this will be 8.5 inch. So 8.5 inch space is now available here, and we have to compute LDC, and we compare that LDC with this length. If LDC is more than this one, we have to provide, if there is a little bit difference, so we provide this hook. If it is greater difference, then we increase the depth of the footing. Remember, thickness of the footing, sorry. So let us check it. Okay, here we have, you see, we can use these formulas as well, because these formulas are used for development length in compression splices. Okay, in compression splices. So here we have FY50. Either we can use this one. The minimum development length basically in compression is 8 inch in all cases, remember. And one thing, here we are using basically number 4 bar, and this is 4000. Okay, and here the LDC we needed as we are using 60,000 psi, so we need 10 inches, remember, and the available space is 8 inches. Okay, so that's why we need to provide hook. Okay, so to satisfy this criteria. Okay, this ends up, okay, this lecture, and this is the check for LDC, and I will explain this development and how to provide this bar. Okay, so explain in Excel sheet. Okay, so here I have basically an Excel sheet. Okay, and in this Excel sheet basically you see here what we have. Remember, this Excel sheet is basically prepared for homework assignments, questions, book questions. Okay, not for frame structures, but I modify this, okay, a little bit in front of you. We have 4 KSI, okay, and we have 60 KSI. Remember, 40 KSI steel is now vanished. It is not used in Pakistan due to earthquake. Okay, and we don't care about these two loadings. We have to change this one. Okay, SDL and SF. This is service total service load, and I think so we calculated this is 72 point. Let me check it. Let me here we have 72.4. So this is 72.4. Okay, 72.4 kip. Clear? And this load is basically we have 106 kip. Clear? And this one is 2000 or 2 ksf, and overburden we have no, because remember this depth which we are using here, this total depth from the ground level to the bottom is assumed to be 4 feet. So as we don't know about the thickness of the footing, okay, so therefore we are using average density of the soil and concrete. So that why here I am ignoring this overburden which is right here, and I basically use 0. Clear? And the unit weight here will be, we are using average unit weight, so 125. Okay, and then side cover sides, that is the size of the column, that is 1 by 1. Okay, here you see it will change. Okay, so okay, now total depth of the footing is, we are using 4 feet. Okay, this is 4 feet, and here we have total depth of overburden is 0. Clear? And now HF is basically nothing. HF is basically the thickness of this footing. So the sheet basically assume that the thickness HF is now the total depth, but we are not using this one. So that why you just we are using basically here is 12 inches or 1 feet. 1 feet. Clear? And 12 inches, because we calculated the depth D, we are assumed that we are using 1 feet. If it is not okay, then we revise again it. Okay, QAN, this is the net effective pressure, and here we have 1.875, and our calculation we are using QE equals to what? QE is equal to 1.5, because they are using 4 times this one, so we have to change this. Okay, how to change this? Remember, we have to now remove this part. Let us see, and what we have to do, we have to use this density, this blue density, and this blue density is basically this one, and okay, and we have to multiply that density with this thickness, this one. Okay, so let me check it. 1.8, still 1.8. so we have 2 kf, clear, and 125 times the depth divided by 1000, clear. So I think so it is okay. QA in, okay, let me check it again. QE is equals to QA, okay, 0.125 times yes, it uses basically h is equal to 4 because average, yes, this is the mistake. Okay, we are using this one is 4 feet, okay, this one, because this is the average density 125, so average density, this height is basically 4 feet. Okay, now 1.5. okay, this is basically QE. QAN equals to QE. Area footing is already automatically calculated. The uses 7 feet is also automatically calculated, and here we have basically the depth. This is the effective depth, and we are using the effective depth as a 8.8 inches, I think so, 8 inches. Now I will show you the difference. Okay, I will show you that this is very important. Okay, here they are using 8.5 inch. Now we are using effective cover 3.5, and they basically what they did, they basically assuming 0.25 clear cover, and then they're using this 1 inch bar. This bottom bar they are using is 1 inch. So if we remove this, okay, and we just write down 3.5 inch, so it will work. Okay, no, we are wrong, divided by 12, okay, to convert it into feet, so 8.5 inch, clear. Now we have to use punching shears, okay, and in punching shear basically this factor is 0.75, okay, and B naught, in our case B naught is how much, let me check it. B naught is 82 inches, so what we have 82 inches, okay, and pi VC is 1322, let us check it. This is 149.9 kip, clear, this is in kip. So if we divide this, multiply with 1000, so we basically, this is 14, and I think so it is close, this is close, okay, this is close, almost this is close. The difference is due to we are using 4 phi, okay, here let me check it. 4, yes, phi 0.75, and B naught is 82, and D is my D 8.5 inch, okay, and this one is, I think so, wrong, clear. We have to, not 4000, we have 60,000 still. Yes, no, I'm wrong, no, I'm wrong. Basically this is FC prime, okay, this is FC prime, okay, this is okay, 4000 psi, clear. So this is close to our calculated value. Okay, now a dash is basically, this is the shaded area, and I already explained this area, okay, that is how much. So QUN is 2.2, this is also okay, and VU is basically 99. This is, I think so, this is total shear, okay, this is total beam shear, clear, and this is beam shear, I think so, this is beam shear. So this is 76.77, this is the bearing shearing capacity in beam, okay, and you see this is A dash, okay, and VUB is basically is how much, let me check it. QUN is okay, QUN is okay, where it is, QU is this 2.16, almost close, okay, and this is 99. So that is the shear which is coming from the due to this loading. Remember, this QU is loading and 99, and the capacity of our concrete is this one, okay. So this beam shear is also okay, okay, beam shear is also okay, clear. So you see this punching shear test is okay. Now we have to use the design of reinforcement. Remember, this is A value, clear, and the A value is basically assumed, that is 0.1 times of H and MU. Now here we have to make changes, clear. MU is basically K35, that is the length times this length times the G27 minus G19 means yes, we have to make changes here because this is L square divided by 2. Okay, this is L square divided by 2. So that why K35 is my K35 is my K35. Where is K35? Here we have this one is this one. Okay, here you see QU in, this is my loading, clear, this is my loading. So K35 is my loading QU and this is my L, clear, this is my L. So if I know already my L, now I have to calculate L because you know that the L is what? The L is basically nothing, it is that length, okay, it is this length, the shaded portion length, and that is 3 feet. Now if I divide this by half, 7 by 2, and minus this length, that is A divided by 2, 1 divided by 2, so I got this length. So let me change this. Okay, so G27, that is my L, clear, this one, and I have to divide this by 2, clear, and closing in brackets. Okay, here we also have bracket, and then minus this one should be removed, and this one is 1 divided by 2, okay, and closing in brackets. Okay, closing in brackets, clear. So and then square it, and this 8 is 2. Now you see 674 pound feet, this is almost 67.46. now if we check here what is the value of MU, that is in inches. So in inches, basically if we multiply 116.8 multiply by divided by 12, 116.8 divided by 12, we got I think so, divided by 12 we got 9.73. yeah, so here we have, if we divide this, we got 67, this is pound feet. So we have to divide, if we divide it by 1000, so 67.46. so what is the region where we have made the mistake? Okay, let me check it. L2, this bracket is, let me do again the calculation. Okay, that where is this error? Okay, first of all I have to use this one, this is L divided by, because we have to square that distance. So L, this is, let close it in brackets, and then divided by 2, so you half the distance, then negative, then bracket, then side of your column, that is 1. Okay, 1 divided by 2. Okay, you need to half them, so that is your critical section length, and then again you have to take square. Okay, so for that purpose, bracket and further bracket, here bracket, and then divide this by 2. Sorry, we have to take square, and then we need to divide it by 2. Let's see again that one. Now what is this value? We don't need this one. So here we got 9.7. if you convert this equals to this one divided by 1000, okay, and if you close this in brackets, okay, brackets, and then multiply it, we have to convert it into inches, so that by 12, so 116, you got the required value. Clear? 116. Clear? This is the way that how you can check the calculation. Clear? And then what we have, we don't need to do this. 0.27 already close to our calculated value, 0.286. So that's why this formula works very well. And remember, most of time teachers object on this formula, and this is the check, okay, because I'm using here head to trial method. And as minimum, now I don't need, I have need to this one because I'm using this one. So here I'm using, remember these are the ACI new version criteria, that if you have using 60 KSI, then your limit is 0.0018, but actually I'm using 0033. So that's why I'm change it, okay, because this is ACI old version, okay, this is ACI old version. And here I have to also make changes. This is my 12 because I'm designing for 12-inch strip, and this is my D, and I think so this D is now this one, okay, D is this one. So here we have, okay, and let me check it. So my AS minimum is 0.34, okay. Now head and trial rule again, revise the calculation, and here you see, and automatically check, okay, there I'm using F formula, okay, and they do the calculation work, and they say that not okay and provide AS minimum, because already we did this calculation, because our AS calculated is less than AS minimum, so that's why we have to use AS provided, AS minimum. And here you see how to use this table, okay. Now as we are using number 4 bar, so that's why I'm check number 4 and uncheck number 6 and number 8 bar, okay. And here we have what, I check this one and I uncheck this one, and okay, clear. So this is the bar area of number 4, and this is, now we have to change this, okay, we have to change this. S prime is basically total area which is provided to the column, okay. Now we are using 0.34, okay, so that is my now required area, and we don't care about this value, okay, we don't calculate number of bars, we are calculating spacing of bars, clear. And here I have to check it, I don't need this 10, clear, so remove this one and check the calculation. So the spacing you need 6.93, clear. And here you have to decide that we are using number 4 bar, and the final spacing will be although in calculation I am using 7, but here I am using what, here I am using 6.5 inch, let's say, okay. So this is my final calculation, number 4 at the rate of 6.5 inch center to center. And here I have dowels. Remember, we check the dowels, whether we need dowels or whether we not need to because we provide dowels to safely transfer the bearing stresses, okay. So this is the area of column, and we don't have this one, we have 12 cross 12, remember we have 12 cross 12, and this is calculated by formula, okay. And here you see this is ACI formula, remember this is phi time, and this P which is we are using in this calculation, I think so 0.7, this is the old version ACI 0.7, but now they are changed 0.65, and this one is I think so wrong, okay. Here we have, yes, this is okay, 4000, so phi 0.85 FC prime into this area. This is one formula for checking the column pi in B, okay. This is the bearing pressure which is transferred from column, okay, which column exerted on the footing, and this is the footing bearing pressure, okay. So here I have to change this one 0.7, okay, although in new version of ACI, okay, we have to use 0.6. So once I change this coefficient, okay, that is 0.70, okay. And let's see that's basically I have to change these coefficient as well. Pi 0.85 fc prime into A. This is the bearing pressure which is coming from the column to the footing, and you see this is multiplied by A divided by smaller a. Remember, this is not a square, this is just only A. A is the footing area, okay, and small a is the area of column, okay. So here you have to insert this formula, okay, in that cells, and this 0.85 fc prime into A smaller a, this is the bearing pressure coming from the column, and the next one is the bearing pressure of the footing. So here I have to insert that formula, and K27 is basically nothing, it is just the side of the column, and I take square and it give me the footing area, okay. And next is 0.7 is change, okay. Now this A divided by A, this is very important. This is defined by ACI that A divided by A under root factor should be less than 2, and once we calculate that factor A divided by A, it is greater than, remember, it is greater than 2. So that's why we have to change this, and we have to plug the value of this as equals to 2. So here I am inserting 2, okay. This is very important, okay. It's defined by ACI. So you have to make these changes. This is very important, okay. If you are using this Excel sheet, I will provide the link of this sheet, okay. So you have to make these changes, and if you are using the advanced version of ACI, so you have to use 0.65, not 0.7. Clear? And the next one is PU, and PU is already known, and from these two you have to select the minimum value. Clear? And the minimum value, I will use the formula, minimum formula equals to minimum formula, that is, no, I'm wrong, I have to find minimum formula, okay. And this is minimum formula. I have to select these two values, and this will give me the minimum value from these two, and now I have to compare basically this new value with that 106. So I converting this in from pound to kip, okay, divided by 1000, and let's see, 342. So 342 is more than 106. That's why our bearing capacity of our column is more than the required one, that is 106. So that's why practically we no need any kind of dowels, okay. This is very important. And next I'm searching for, okay, so here I have I write down that PU is less than my pi P and B, that is bearing pressure. So that's why we are safe. We practically no need of dowels, but and you see that no need of dowels. I insert F formula, okay, here. So you understand how to use F formula, okay. If you don't understand, please watch this. And similarly 0.005, okay, this is ACI minimum criteria for dowel. You have to use 0.5% of the area of the column, and therefore I am inserting that the actual formula, that is this factor 0.5 divided by 100 give me 0.005. So I multiply 0.005 with A, I got 0.72, and now A is my 0.72 is, remember, this is important, this is very important, okay. As we are providing 4 bars, this is my ASD, okay. Now I have to check this ASD dowel area with my column area, column reinforcement area. So as we provide basically in column 4 number 6 bars, okay, where they are, let me check it. Yes, there we are providing 4 number 6 bar, okay. So 4 number 6 bar will give me how much area, we have to determine it, okay. We have to determine it, and that area will be 4 okay. These are the dowels, okay, and now these dowel must be consistent with the reinforcement of the column, okay. So the dowel area is 0.72 and the column cross section bars which I'm providing, that are 4 times 0.441. okay, you need to